With code number 1325, delete leaf with a given value. This is medium question. Let's get into it. Given a binary tree root and an integer target, delete on leaf node with value target. Note that once you delete a leaf node with value target, if its parent node becomes a leaf node and has the value target, it should also be deleted. You need to continue doing that until you can. Okay, let's check with example 1. There is leaf node and then target is 2, so this 2 is deleted. And then now this one is not leafed, but after deleted one and then delete one become leaf node, so this one also deleted. So finally we needed to return this 3. Actually this one, okay, let's check with example 2. This is leaf node and then target is 3, so deleted this 2. In this case, this leaf node and then this one turn into leaf node and then deleted and then turn into leaf node. So finally this one is left. All is deleted, right? Okay, how we can do it? How to check leaf node? Yes, leaf node is left and right node is known. All of left right node is both left and right is known. That is leaf node, right? And then one, so just first we found the leaf node and then check the value is 2. If true is, I will delete it, and then after that I will check this one too. So I gonna use the recursion and bottom up approach because we need to check the update from here. Okay, let's check with the code. Okay, let's implement code. First I need to helper df and then node, then base case is if node is none and return, and then let's find the leaf node. Node left is none and node right is none, and value, node value is same as target. We need to delete one, so I will return none and then I will receive it. Node left is helper, node left, and node right is helper, node right, and then I will return helper and then argument is root. But there is one problem, that is we needed to delete the node and then this one become 2 leaf node. So if this is 2, we also delete recursion. How we can do it? Yes, that's right. There is very simple way. So we just check delete is last. That means after going to here and then popping node and then checking, and then after popping, checking, popping, checking, popping, checking. Then finally, after popping, we will check this one is okay. I will show you. In this case, first we check to here none and none, and then popping left node is none, right node is none, and then this one is leaf node, and then we will delete this and then popping. In this case we are also checking this is the leaf node. Yes, because it already updated to n. This one is already n, so checking to delete and 2. This is the benefit of the bottom up approach. So let's check the code. Okay. Okay, there's some bug in here. Okay, let us helper node, node is no, return, and then left node left, right node right. If node left is none and node right is known, and node value is target. Return node. I didn't return. Itself. Return node. Then return node itself, and then whenever left or right, it will update it. Please don't forget this one. That is very easy to forget. Now it's okay. Good. Awesome. Okay, let's check the time complexity. Actually, it will traverse every node, and then it take linear time with the linear space, because we use the system stack of recursion. And then worst case, the system stack is same as depth of node, and then worst case, when you just screw the node left or right, and the depth is same as length of node, count of nodes. So we can say space complex is linear space. Thank you.